An important class of materials have properties intermediate between rigid solids and simple fluids. They display behavior that can be surprising when we study it carefully. These materials are generically called soft matter. Examples include rubber and many biomaterials used to construct living organisms. Soft matter resembles fluids, such as air, in the sense that thermal effects are important. Think of the ideal gas law. But soft matter also resembles solids, such as steel, in the sense that its molecules have some permanent structural arrangements that also contribute to its properties. Here is a thin sheet of rubber, a balloon. We can observe small changes in its temperature by viewing it with an infrared camera. When I stretch the rubber, it heats up. This by itself may not be surprising. I did mechanical work, which often leads to frictional heating. The first surprise is that when I let the stretched rubber come back to room temperature, then suddenly release it, it gets colder. We might have expected that here too. Mechanical work is being done by the rubber on my hand, and so again there should be as much frictional heating as in the stretching. Why is that expectation incorrect? We can get some insight when we notice that compressing a gas requires us to do work and heats the gas, whereas releasing it to expand delivers work back to us and cools the gas. But what is the connection? In what sense is stretching rubber analogous to compressing a gas? In what sense is rubber more like air than it is like steel, which has no strong connection between mechanical and thermal behavior? To make progress, we need to appreciate the underlying structure of rubber. It consists of molecules that are themselves long chains of many atoms. Each molecule is partially structured. Chemical bonds create a permanent chain. But each molecule is also partially unstructured. It's floppy and can twist and coil in many ways. When we stretch rubber, we decrease its randomness, partly straightening out each molecular chain. When we compress a gas, we also decrease randomness, confining the same number of randomly moving molecules to a range over a smaller volume. Either way, thermal motion opposes this increase in order, which is why rubber resists stretching as air resists compression. When we allow a gas to expand, mechanical work gets done on the walls of its chamber. The only available source for this energy is the random kinetic energy of the gas molecules, commonly called heat. Similarly, when I allow stretched rubber to contract, work gets done on my hands. Again, the only available source for this energy is the random kinetic energy of the rubber molecules, so the rubber cools. The argument just given makes an interesting prediction. The ability of stretched rubber to exert a retracting force must be connected to how much thermal energy is available. That is, it's related to temperature. Thus, if we hold stretched rubber at a fixed extension but heat it, its tension force should go up. We can use that observation to create a simple heat engine. Just as alternately heating and cooling a gas can give rise to forces that do net work, we can also do the same using alternately heated and cooled rubber. In this demo, a metal ring is suspended from an axle by 6 rubber bands. At any moment, half of the rubber bands are in the beams of 2 heat lamps while the others are shielded. As each rubber band moves into the infrared beam, it contracts slightly, unbalancing the wheel. The unbalanced wheel then rotates, bringing a new rubber band into the beam, and also moves a band on the opposite side out of the beam. Our first demonstration showed how soft matter can generate or absorb heat based on imposed mechanical changes. The second one showed, conversely, how imposed thermal changes can alter mechanical forces.